Good evening, ma'am. This is Rutba Farzah from Triple Department. My CAA 2 assignment of circuit analysis 1 is parallel resonance. My bearing roll number is 244 G1A0 244. Today my topic is about parallel resonance. So let us understand about parallel resonance. The introduction of parallel resonance. Parallel resonance is a condition in circuit electrical circuit where the inductive and capacitive reactance are equal. The phenomena occurs in a parallel RLC circuit affecting the entire impedance and frequency resonance. Understanding frequency resonance and parallel resonance is a circuit for assigning effective electronic systems. Basic components of resonance. Resonance occurs when the energy occurs uh, oscillation between inductance and capacitance in resonant circuits and total impedance in minimizing resonant frequency formula. The resonant frequency formula is F naught. In parallel resonance, RLC circuits can be calculated using this formula. F naught is equals to 1 by 2 pi root of L into C. Here L is the inductance in Henry, C is the capacitance in Faraday. This formula highlights the inverse relation between frequency and the square root of products of L and C. Impedance at resonance. The impedance at the impedance the total resonance at resonance the total impedance of parallel RLC circuit is at its minimum. The impedance can be calculated using this formula. Z is equals to RS parallel to 1 by JLW plus J omega C. This results in purely resistive circuits at the resonance frequency at as the reactive components cancel each other out. Quality factor Q quality factor can be defined as QF, or Q is a measure of how impedance a resonant circuit is. The quality factor is measure of how underdamped a resonant circuit is. If it is defined as Q is equals to F naught by delta F, where delta F is a bandwidth of the circuit. The higher quality factor inducts a harrow, harrowed bandwidth of greater selectivity at resonant frequency. Current behavior in parallel resonance. At parallel resonance, the current through the circuit reaches in minimum value. The inductor and capacitor exchanges energy resulting in minimal energy loss. These characteristics makes parallel resonance favorable in turning applications. Applications of parallel resonance. Parallel resonance is commonly used in radio frequency. Radio frequency is also known as RF for the circuit turning in and turning. It also empowered in filters to select a specific frequency while uh, attending others. The additional parallel resonant circuits are found in oscillators, and single processing circuits. The application, the bandwidth of parallel resonance. The bandwidth of parallel resonance refers to a range or range of the frequency around the resonant frequencies. It is determined by the resonant values. Higher results in a wider bandwidth. Understanding bandwidth is critical for applications that require precise frequency selecting. It determines the resonant values. Higher resonant results in a wider bandwidth. The bandwidth can be parallel or both in series and parallel ranges. Understanding the bandwidth for applications that requires prices frequency selections. The damping in parallel resonance. Damping refers to the reduction of oscillation amplitude over time in parallel resonant circuits. Damping is influenced by the resonance resistors values, and proper damping ensures that stability in circuit operations, preventing oscillations from becoming excessive. The damping refers to the reduction of oscillations in circuit resonance. In resonant circuits, damping in influencing the resonant values. Phase resonance in phase relationship in parallel circuit. In parallel resonance, RLC circuits. In parallel RLC circuits, the phase angle between current and voltage is significant. At resonance, the phase angle is zero, inducting the current and voltages are in phase. These conditions allows for minimum power transfer within the circuit. Is called as phase relation in parallel resonance circuits. Compa- Comparison with series resonance. Unlike series resonance, where components are connected in series, parallel resonance features components connected in series. This series resonance is results in maximum voltage, while parallel resonance yielding in maximum current. Both configurations are important in different applications based on their characteristics. Stimulation tools for analysis. Various stimulation tools such as pieces can be model parallel resonance behavior. These tools allows for visualizing of circuits of different frequency. Stimulation are essential for predicting frequency before physical impedance. Practical consideration. When designing circuit components, tolerance can be affect resonance characteristics. Environmental factors such as uh, temperature can also influence circuit behavior. Circuit careful consideration of these factors is necessary for reliable circuit performance. Conclusion is parallel resonance is the fundamental concept in electrical engineering and electronics. It plays a vital role in turning, filtering, and auxiliary designs. A through understanding of parallel resonance enhances the ability to design, affect, and a circuit feels free to modify any of the component as per your specific needs.